here is a supplementary video for our Tele1022 Lab 2, the shifting and summing or level shifting and summing amplifier for the lab prep. Now I have changed some values so I can just show you the process. However, you're going to have to apply the values that are listed in the lab sheets in order to do your own calculations. All right, so that's this is this node right here. Okay, now the changes were made. Originally the V supplied, the voltage supplied, the positive and negative rail is 15 volts, plus and minus 15 volts, but for this example we're going to use plus and minus 9 volts. And originally in the lab, the DC offset of the output is listed as between 5 and 10 volts DC. And in this example, we're going to set it up for, we're going to aim for between 3 and 6 volts DC, and that is by regulating this potentiometer, R3 right now. And we have known, what's known is that the R3, the pot, is equal to 10 kilo ohms. Now, the idea is to calculate RF, R2, and R1. So on the output, we're going to have 4 volts peak to peak. And the voltage, the middle of the voltage, okay, the voltage is going to be offset. The AC 0 point of that waveform is going to be with the DC offset between 3 and 6 volts. All right. Now it's 1 volt peak to peak, and I have listed here 0.5 volts peak value, so just keep that in mind here. All right, now what do we have here? Let's analyze this circuit a little bit, shall we? We have the power supply connection. Negative 9 volts is going to go to the negative power supply pin, negative rail of the op amp, and the positive 9 volts is going to go to pin 7. I couldn't switch those on the multisim because I grabbed this thing from the multisim. I had to set up the circuit on the multisim, and then I just took a screenshot. So in order for me to flip those, I would have to, this would flip as well, and it wouldn't just wouldn't look as good as it is, as clear as it's now. So just keep in mind, the top one here is negative volts, negative 9 volts, and the bottom rail is here positive 9 volts. Just don't forget that. And here we have the virtual ground, which is the middle between the midpoint between those two power supplies. Over here we have a signal generator with 1 volt peak to peak, which is half a volt of peak value. All right, and we have 1 kilohertz. That's a pretty good friendly frequency for our purpose. Now, with the negative feedback, so here we have the negative feedback between RF and, well, the rest of this whole thing. But for the signal, what we have, what counts for the signal gain, because we have 1 volt peak to peak, and we want to have 4 volts peak to peak here. So obviously we want to have the gain of 4. So we know that the relationship between this resistor and this resistor is going to be 4 to 1. So 4 to 1 ratio between these two. We don't know the values yet. We only know the value of this resistor. And the DC offset is going to be regulated by R3. And by regulating that, we're going to be adjusting the DC offset of the output waveform. So the 4 volts peak to peak waveform is going to move up and down with its midpoint between 3 volts and 6 volts. Okay. So that this little network of resistors is connected to the negative. So it's between this part here and this part here. It's a summing amplifier as well. So this one side of this R3 resistor potentiometer is connected to also to the inverting input, and through R2 it is connected to -9 volts. All right, so here's the analysis. Now let's get to the solution. We want to have 4 volts peak to peak, so let's write it down here. Make things nice and clear. Skip no steps because well, this is actually a pretty cool problem to solve. But in order to not make a mistake along the way, it is a good idea to just not skip the steps when writing things down. All right, so voltage, the output voltage, or the output waveform should be 4 volts peak to peak. We got it. And it is, we just wrote this thing down here. The DC offset of that waveform is supposed to be between 3 and 6 volts DC by regulating R3 from 0 to 10 kilo ohms. Let's write that down as well. All right, let's write this down here. Power supply equals, just so we don't have to keep things in the back of our head. It helps a lot. Power supply from plus to minus 9 volts, and we know that R3 equals 10 kilo ohms. So here is the scenario here. All right, let's take a look at step 1. Write things down. Step 1, that's the relationship between V out and V in, because we know this voltage here, and we know what this is supposed to be. So 4 to 1, write it down. So the relationship between these two resistors is supposed to be 4 to 1 in order to give us the voltage gain of 4. All right, we have this thing jogged down, no problem. Step 2, we're going to have to see and be clear about what is going to happen to the output when we move this resistor to the maximum value and when we move the resistor to the minimum value. So let's just establish that and put it on paper so we don't have to think about that and try to remember, and because of that we can make a mistake along the way. Step 2 here. All right, establish the relationship between V output, the output voltage, and resistor R3. All right, so right here, if R3 goes down, the value, then the input voltage is going to go down. How is that established? All right, we're looking at those rules. Amplifier op-amp rules. No current flows in and out of the outputs. All right, we know that. That's just how the op-amp behaves. Now, under the condition of negative feedback in place, the two input voltages, the potentials, are going to be equal. There's going to be no voltage between the inverting and non-inverting input. That's the rule if there's a negative feedback. And if, because here's the rule 3, or the point number 3, if the calculated output voltage is greater than the supply voltage, then this rule here no longer applies. We'll get back to that. To that condition at the very end of this video here. Right? All right, so no current flows in and out, and the input voltages are equal. All right, that's a good starting point. So this network right here of resistors, right here, because we have established this the relationship between RF and R1, so forget about that, because now we're going to take a look at anything else but that. So if there is no current flowing in and out, so the voltage divider can be just, we can skip the amplifier here, skip that because there is no current flowing. So the current is going to flow from here, well, there's going to be RF, and then there's going to be this here, and there's going to be that along the way. Then there's R2 along the way, and there is well, don't forget that the end of that is connected to -9 volts. So we can redraw this part from here to here, just like that. All right, here's the output voltage, here's the RF, here's that V in. It's there, but we're not going to we're pretty much all going to ignore that, but we just want to have that there. And here is the R3 resistor 3, the potentiometer, and we have that resistor R2. I didn't mark it. All right, so what happens if we minimize the value or bring it down to 0, if we lower this value of R3? So it's almost like well, there's not going to be any resistor here, which is going to cause this point, if this point goes down, then this point is going to be closer to the bottom rail, so that point is going to go down. And because we are plugged into the inverting input, then the voltage on the output is going to go up. Okay, so we have established that if R3 goes down, the out goes up. And by the same logic, if R3 goes up, then we're going to have the output voltage go down. All right, so what's the top DC level that we want? The top DC level we want 6, so we can just put that 6 here, and we can put that 3, because this is the upper limit and this is the lower limit of our shifting of the midpoint of the DC offset of that waveform. All right, so here is the output. Okay, so if this goes down to 0, then we want the output to be 6 volts. We had to establish this just so we could come up with this relationship and write it down on paper. Now, if R3 goes the other way, we regulate that. If it's maximum, so it's 10 kilo ohms here, so it's in place, then we want the output voltage to be 3 volts. All right. Write it down so you could come back to it. So, step 3. Now, let's take this thing a little bit deeper here. While the where R3 is minimum, which is 0 ohms, we can redraw this circuit as this here, because that is not going to exist. It's just going to be just a piece of wire. So here's that, and now we can plug in the value here. So here's the 6 volts, because we know that with R3 0, we're going to have 6 volts here. So let's put it down. So that's what we're going to have, and here's -9 volts, so here's that. So we're going to have that kind of network happening here. So we have 6 volts, 0 volts. Why do we know that this is 0 volts? Because of this rule number 2. Input voltages, voltage potentials are equal, and we have that at 0. So when we have the negative feedback in place, the output voltage is going to try to do anything that it can to bring that thing to this thing. All right, a lot of things here. So now we know that this is 0, because this is 0. Rule number 2. Okay, so let's go. All right, so now we have the voltages. Well, what can we do here? We have a voltage divider, and if we take the absolute values of the voltages, we can come up with the relationship. That's going to take us, well, anything that we can fish around for. We can fish around for the for possible relationships, possible whatever we can find. Write it down. Maybe we can use it later. Let's see. All right, so with this voltage divider set up this way, and if you take the absolute values of those voltages, so here is the absolute value of this voltage is 6, and the absolute value of this voltage is 9. Forget the minus for now. So this way here we can establish the relationship. Now here, the absolute values, 6 to 9, this voltage to that voltage ratio is going to be equal to the ratio between these two resistors. So let's write it down. All right. 6 to 9 is going to be equal to the same ratio as if we divided RF by R2. RF by R2. And we can reduce this fraction here to 2/3. So then, based on that, we can establish two relationships, see if we can use that later on. Maybe we can, maybe we can't, but it exists, so let's write it down. All right, so based on that, RF equals to 2R2 over 3, right? Because here, RF from those proportions here, this equals this times this over that. Okay, this times this over that. And by the same logic, R2 is going to be equal to this times this. Just go diagonally and divide by what's left here. All right, so here we have those two relationships. Write it down, keep it for later. Maybe it's going to come handy. All right? I got a feeling that maybe it will. All right, next step. Because we have established the relationships of whatever we could while R3 equals 0. Now let's see if we take R3 the other way, the potentiometer, all the way to 10 kilo ohms. Then we're going to redraw the circuit as such. This is just a symbol here. We don't have the wiper halfway. It is going to be that way. We could just forget that this wiper exists. All right, so what do we have? We have that now we have 3 volts because of this here. All right. We just have to not forget any kind of steps. Don't make a mistake, because anything can set you off here to the wrong final calculations. All right, so now we have 3 volts with this resistor being at the maximum. And now we have the value here of 10 kilo because it's a maximum. And it's still here. We have the 9 volts. And this doesn't change because this not inverting input is tied to 0, which means this is going to be 0. Right? Rule number 2. Okay, so what can we do here? Same thing, proportions. Absolute values of this voltage here. So here's 3 volts between here and here. And there's 9 volts between here and here of absolute values. So we forget the signs, minus or positive. Absolute value is just absolute value. All right, so we have proportions. This part here, this resistance, and this total resistance. And we have this voltage and this voltage, so we could establish the proportions. This to that is same as this to that. All right, this and that. All right? Okay, let's write it down. RF to R2 plus R3, there you go, equals to, well, 3 by 9. And then we can reduce that to 1 over 3, 1/3. All right. I just wrote it here so we don't have to look at that. 3 by 9. Okay. All right, so what can we do with this thing here? We have the RF, we got our 2, let's see what we established. Oh, we got these two. Can we do anything with these two guys here? Well, what if we substitute the RF, because then we're going to have just one unknown, or reduce the number of unknowns, and see if we can reduce the whole expression to have something that we can use actually to our advantage. All right, so let's substitute the RF, this thing here, to the expression that we came up at step 3, in step 3, which is this thing here, right? Because there's R2. Well, all right. And I just wrote it down here, what it is. So instead of RF, we're going to have that expression, which is 2/3 of R2 over R2, right? Or, well, we started here. 2/3, here's RF. That's RF, which RF right here, okay? Right here. So we just put, instead of RF, we put that here, that expression established in step 3. And we wrote it down, but it looks kind of, well, not as pretty, okay? But let's write it down as it is, all right? So here, and we leave the denominator as it was, and that is going to be equal to, well, 1/3 right here. Then we can take it further. We can change this expression, how it looks, to this way, all right? So that's going to be here. The denominator stays the same, and that equals to 1/3. Now, if we divide both sides by 2/3, which is going to be the same as multiplying it by 3 2's, both sides, we're going to come up with this here. All right, we're going to get rid of that. But then again, in order to keep the sign, of equality, then we're going to have to multiply this by 3 2's, which is dividing it by 2/3, right? All right, so we have that, and as a result of that multiplication, it's going to be, 3 times 1 equals 3, and 2 times 3 equals 6, 3/6, which is 1 tooth. All right, okay. Tooth fairy comes to mind. Okay, never mind. Okay, so now we have that. So let's just kind of clean it up a little bit and see what it looks like. R2 equals to R2 plus 10 kilo, what is it here, over 2. This is just, this here is basically derived from that. It's just rearranged, okay? Keep going further. Then that means we can just keep reducing it further. R2 over 2. I just kind of split this thing right in the middle here. So this here equals this here. All right. Okay, making things a little bit clearer, and we still have R2 on the other side of the equal sign. We can do something with that. Right? Well, what's 10 kilo by 2? Well, that's 5 kilo, so we'll just put it here. All right, so that helped us out. Then what we have here, R2 over 2, that is just going to give us, R2. Half of R2, okay? R2 over R2, we'll just keep that here. And there's R2, that's the same thing here. I just made a mirror image. I just put that on the other side of the equal. Now, what happens if we subtract R2 over 2? Remember, don't forget there's 2 here. So if we subtract this from both sides, we're just going to bring it over there. And that is going to give us a nice solid number to work with on the other side of the equal sign. So over here we still have some sort of expression. Over here we have a solid number. Well, we're getting somewhere, okay? All right, so from that, by that action, we're going to get that. R2 minus R2 over 2 equals 5 kilo. All right, what can we do with this? Can we reduce that to anything? Well, what's R2? Let's have two fractions here so we could do how. So R2, we can express that with 2R2 over 2, which is R2. Well, now we have two same denominators. So we could do something here. Equals 5 kilo. And that is going to give us this here. And look at this. R2 over 2 equals 5 kilo. All right. So 2 times 5 kilo, because R2 equals, because we're going to multiply both sides by 2 now, so we can know what R2 is, because here's a solid number and here's a solid number. We're going to have on the same side of the equal sign. Why not? And that is going to give us R2 equals, well, because multiplied by 2, so that's going to stay as R2, and this one multiplied by 2 is going to give us 10 kilo. Oh, look at that. R2 equals 10 kilo ohms. Whoo, we got it. Okay, so we got the solid value for R2. So we know now that this resistor equals 10 kilo ohms. Do we have any of the other relationships here? Oh, look at it. I think we wrote something down somewhere here. Oh, look at this. So we know what this value is. So now, basically, we know what RF should be, because we are going to apply this expression here. Hey, why not? All right. What is that going to give us? Well, calculate RF based on the expression that I just showed you in step 3. So here's the formula for that we established. RF equals 2R2 over 3. Da-da-dum, da-da-dim, bada-bim, bada-boom. Boom. We have that number here. So put it down and kind of put it in a frame it, so we could quickly find it with our eyes when we're looking at the pages. Right? Okay, so now we have R2 and RF, and we established the relationship between RF and R1. That is 4 to 1. Now we know what RF is. Hey, we can calculate R1, what it is, and it's 1.67 kilo. So if we want to use real existing parts, we could come up with this resistance here. So R1, 1.7 kilo, and now we have the values. Write them down in order to establish what we wanted. These are the values of the resistors. Okay. All right. Well, let's connect this thing. You're going to connect this circuit, but you're going to have your own calculations for the other values, and you're going to have the values that you're going to calculate. That's going to be funny when you notice something when we get to the classroom here. And once you assemble the circuit, once you get your own calculations. All right. Now, let's multisim it. So I'm just going to bring up my multisim. Here is our circuit on the multisim. And I just kind of wrote these rules here just so we can, because I want to show you something. Right? All right, so now plug in those values. I just plugged in those values, but I just didn't, well, why not? Here, now we know what the values should be. Show values. Boom. There you go. Now we know what this one is. Show values. Now we know what this one is. Show values. Here. And now we know what this value is of that resistor here. Okay. Now let me, yeah, I'm going to just leave these connections like they are here. Just going to get this thing out of the way so it's not messing up the view of our connections here. So same thing here. We got minus 9 volts going to pin 4, plus 9 volts going to pin 7. And here is our regulation of the potentiometer of R3. And here's our scope. So let's bring the scope onto display. And let's turn the simulation on. All right, so here we have 4 volts peak to peak. Trust me, it is 4 volts peak to peak. What I could do is I could bring the cursors and prove it to you, but it is 4 volts peak to peak. All right. Let's not make this video longer than it should be. Now, let's see if we can regulate this potentiometer and see if this thing moves up and down the way we want. See, that thing moves up. So that is 6 volts here. Well, it looks like 6 volts because look, It's 5 volts per division for channel 1. That's the yellow waveform here. So the middle of that looks like it's 6 volts. It actually is 6 volts. Now, it should go down to 3 volts if we take that to maximum. Boom, that's 3 volts here in the middle, and the waveform moved down. It didn't change. The waveform didn't change. It just moved up or down. Now, what do I have on the second input? Where did we connect that? Second input of the oscilloscope goes right here. Well, just to prove that it is equal to 0, and this is our 0 point here. So that blue line is channel number 2, which just tells us that with the negative feedback here, okay, and we do have the two inputs at the equal level, which should be at 0, because this here is at 0, so this one should be at 0. Now, let's do something funny here. Ha funny. Okay, let's do ha funny. Here's that point right here. If calculated output voltage, if whatever we're going to calculate based on our calculations, if based on our calculations, the voltage on the output should be more than the supply voltage, either way, then this rule no longer applies. So if we can make that circuit to try to output more than the supply voltage, then at some point we're going to see some voltage differences, potential differences between those two, because then it says that rule number 2 no longer applies. Can we do this? Excuse me. Yes, we can. All right. What's happening here? So we got a half a volt at the highest point. Let's see what the highest point that this thing will try to go, the output is going to try to go. At the highest point is going to be 6 volts of the DC offset. So the middle is going to be 6 volts, the middle of the waveform, the midpoint, the 0 reference of the waveform is going to be 6 volts. And plus, because it's a summing amplifier as well, at this point here, plus, well, here's a half a volt times 4, so plus 2. So at the highest point, it's going to be 6 plus 2 is going to give us 8 volts. It is still less than plus 9 volts, right? Well, then rule 2 applies. What can we do? Well, we can play around. We can increase this here to make it so it's going to try to go further than that. Very easily we can do. We can just double this voltage here. We can make it 2 volts peak to peak by increasing that. So it's going to be 1 volt. It's just, over here is just asking for the input as of peak. So 2 volts peak to peak is going to be 1 volt peak. So let's change that number. Oh, of course. We're going to stop the circuit. But now I'm going to take this thing down because, all the way up here. So that thing's going to be the lowest. At the lowest point, we're just going to see this thing bigger, this waveform bigger. But still going to see look what happens when we regulate that and make that output try to have more than the supply can give. All right, I just have to stop simulation for the changes to take place. Okay, let's start the simulation again. All right, we have a bigger waveform. Now, the difference of the potentials is still, well, there's no difference of potentials. The voltage between here and here is 0, and that shows on that blue line, which is connected to channel 2, which is connected here. All right, because we have 3 volts plus 4 volts, because 3 volts is the middle of that is 3 volts, and the highest point right here is going to be, well, we got 1 volt peak, times 4 is going to be 4 volts. So 3 plus 4 is 7, still less than 9. But if we move that up, we're going to overcome that. We're just going to go further than we can. Let's try it. See what happens. Gonna make it up, going up, going up. See the waveform moving up? I'm doing it slowly, and somewhere around here. Oh, look, it's going to start clipping. See that? I backed up a little bit. Go up. All right. Boom. At this point right here, it says if the calculated output, this is the real output, is going to clip because it can't go any further than 9. Right? But it will try the calculated voltage. If we do the calculations with the gain, voltage gain, and the values that we have, it is going to be more than 9 volts. And it says rule number 2 no longer applies if the calculated voltage is going to be more than the supplied voltage. And look, it's true. We see the difference of the voltage at that moment when this thing is trying to. So we have the clipping here. Is it at the same point? It doesn't look like it is, but you know, it could be an optical illusion. Let's bring this position down here. I'm just going to bring it down just to show. Actually, here, I'm going to bring that down. Look, it's happening exactly at that point. That the voltages, these voltages are no longer equal at this point. Right? So here, you know, everything, all those rules, yeah, they are truth. They are true. All right. So this is how we solved that circuit. I think it was pretty cool the way. Thank you, Mr. Habinski. I would give them something easier to solve, but I'm glad you gave them, you come up with this example because it's just a really satisfying piece of math to, or a sequence of events that we need to put together that we can actually come up with those values for these resistors. All right, so this is how you do this one.